Good afternoon. Come on in from the back. You're still straggling in. You successfully found this room, so you've completed the first leg of this adventure today. My name is Bob Ward. I'm a principal escalation engineer at Microsoft in customer service and support. The talk is today inside SQL Server Latches, and it's 90 minutes. It's not doesn't list it as a spotlight talk, but it is 90 minutes. Today, you're either going to hear a bunch of stuff that you haven't seen before, or a bunch of stuff that you have no idea what it means. If I can meet somewhere in between the middle, and you can hang on for 90 minutes, I think you'll like what we're going to show you. If that's not what you want to do, you're not going to embarrass me if you want to walk out and go find another talk. So we're going to move pretty hard and fast. A lot of my talks have a lot of information, a lot of internal information, but I think you'll like what we're going to do. So a couple things about CSS at PASS if you haven't figured it out. We're always at this conference. We have a lot of involvement. It's hard for me to advertise these other talks because I'm the last one on the list that's actually speaking at the conference. But we have a lot of great individuals here, especially in the BI space. Adam Saxon, Evan Basilick. I've done some great talks in the BI during the pre-con, during the main con today. And a lot of people in the SQL Server Clinic. How many guys have you been to the clinic? Okay, so everybody didn't raise their hand. Go to the clinic. If you've got something that you've never been able to figure out, need help on, we have a lot of our great guys, the CAT team and the CSS team at the clinic. For me personally, unfortunately, this is my last day at the conference. I've got to fly back to Texas. High school sports beckons for my kids. So usually after my talks, I try to go to the clinic to answer a lot of questions about my talks, but I won't be there tomorrow. But that's okay. So if you'll send me an email after the talk or weeks after, bobward@microsoft.com, be happy to answer your questions about my talk. It doesn't mean it's a free support call or my server's down, Bob. Would you come to my site and fix it? But what I'll do is I'll compile those questions and post it on our blog. So about this talk this year, I did something a little different. I sent an email to the MVPs, and I gave them a list of choices and said, hey, what do you guys think I should talk on this year? So I gave them these choices. And the number one choice was inside Latches, inside SQL Server Latches. And when I saw those back, I kind of scratched my head and I said, really? That's what you guys really want me to talk about? And I'm thinking, all right, sure, it could be painful. Really get into it. And every year when I do a talk, I always show my slides to my wife, Ginger. She looks at my slides, she goes over the spelling of them, looks at the grammatical stuff, and every year she makes the same comment. She says, Bob, this is really interesting. I have no clue what you're talking about, but you didn't say anything stupid in the slides. But every year she also says, what do you guys do up in Seattle? And I said, well, I'm doing this talking inside Latches. I've got a lot of people said it's really exciting about it. I told her last night on the phone that a couple of people came to the clinic and said, Bob, I love your talks. I have no idea what you're talking about, but they're great. To which my wife responded, I know there's something really wrong with these people. So you've joined an elite club of people that are really insane. So one important point about the talk today, 2 points. One, because I got so much stuff to cover, I'm not going to take questions in the middle of the talk. But I will stay here, at the end of this thing, until we have to, walk over to GameWorks, I guess, and answer your questions about Latches. And, of course, take your emails. And a lot of stuff I'm talking about is actually undocumented. Not because it's NDA or I'm going to get in trouble from Microsoft for showing this stuff. The important point is that there's a few things about the internals of how Latch works that may change in the next release. You can count on the fact that it works with 2005, 2008, and R2. But in the future, if you start doing the bit twiddling I'm going to show you today, it may not work in a future release. So I'm just giving you that warning up front. Don't call CSS and say, Bob Ward, show me how to break a bitmap out of a Latch class, and I don't get it. It doesn't work anymore. So let's get right to it. What is a Latch? Well, in SQL 7.0, we had this new concept we had to introduce. It's called row-level locking. So no longer could we rely on the fact that one thread can only access a page at a time. So we need to introduce a new concept called a latch. And we did it specifically for database pages in SQL 7.0. And we still use that concept today. You may have heard somebody talk about the fact that it's physical protection versus logical protection. Well, what the heck does that mean? Well, basically it comes down to this. We need thread synchronization for important structures, our currency-sensitive code. And often we use a latch to do that. Now, what's logical? Well, logical is more of an application thing. Locks, right? There are isolation levels, there are transaction semantics, things of that nature. But for latches, we have none of that. In fact, latches are almost, in a way, database independent. Yet almost every database vendor has locks, right? So some other important features of latches, there's ownership and waiters. It's a similar property to locks, though. There's structure to how we use latches in the system. Particular threads can own latches, and we have a list of waiters waiting on latch to protect these structures. In addition, we have a compatibility matrix, or modes we use for latches like locks. We have things like exclusive latches, shared latches, update latches, things of that nature. So again, similar structure how locks work, but again, it's different or independent from the actual database, relational database concept. And the most important point of all about latches is you really don't have any control over this stuff. There is no such thing as a latch hint in SQL Server. You can't say select star from my table, option equals latch sh. That's not possible. Of course, it doesn't actually make any sense. So why do you even care about this stuff? I mean, why are you even here today, besides the fact that you want to be confused, as you've mentioned to me several times you like? Well, as it turns out, there are factors under your control that can affect the visibility and behavior of latches, such as things you do in your application. You might write queries inefficiently in such a way that might generate maybe an excessive amount of I/O that could lead to maybe something called an I/O latch you're going to see. You might design and configure the database in such a way that could lead to latch contention on things dealing with things like autogrow. And then finally, the point about I/O is really important. One of the great ways to see whether you're having I/O contention in SQL Server is to look at a concept called the page I/O latch, which I'll talk about today. So where do you see this stuff? Where does the visibility and behavior actually come from? Well, first and foremost are these 4 DMVs that you might see in the system. The first two you've probably all seen before, OS wait stats and OS latch stats, dealing with statistical historical information about the cumulative weighting on different types of latches. And of course, I've pointed out the command here, dbc SQL perf, where you can clear those stats at any time. And then primarily, when you're looking at kind of a live system, you might look at sysdm exec requests and sysdm OS waiting tasks, and you'll see latches show up in the form of a wait type. We'll show you an example here in a second. In SQL 2008, we introduced extended events, and I'll show you later in a demo that there is an actual X event that can track information about contention on latches. And then we have perfmon counters, where you can do more statistical information about the average wait time of latches and how it affects your system. And then finally, at the very end, I'll talk about what a latch timeout is, which if you ever get that in your error log, that's a very bad thing. I'll explain why that is later. Let me flip over for a second and just show you a couple things about these DMVs I want to make sure you understand before we get going today. Okay, so I've got here a couple of queries. One of them is against sysdm exec request, and I'm just pointing out some of the more common columns I normally look at. So when you look and see latches that show up in exec request, you're going to see a latch show up in wait type. If it is what's called a page latch or a buffer latch, it'll actually say the word page latch, or we'll find out later what an I/O latch is, or page I/O latch. If it's a non-buffer latch, it'll say the word latch _ mode, and I'll show you an example of what I mean by that later. The wait resource gives great information about what kind of latch we're waiting on. If it's a buffer page latch, you'll have a page ID. If it's not a buffer latch, it'll be some name that you probably don't understand what it means, which I'll explain more, some examples in the talk. And of course, you have your wait time. Now, what's interesting is that if you look at DMOS waiting tasks, you get some additional columns that are slightly different than up here. For example, in the wait resource for a non-buff latch, you'll have some sort of hexadecimal address. I'm going to show you later in a demo how you could actually use that to look at something about the latch. Whereas the OS waiting task, we break that out into the actual resource address and a description of the type of latch it is. Now, does anybody know why it might be important to look at OS waiting tasks versus exec requests when I'm looking at contention? There's one specific reason why you might look at this, because there's information not in here about your contention. Does anybody know that? Parallelism. Thank you. Adam Mechanic, front row. I'll sign your little card to get you a connect or whatever after the talk. So the reason is parallelism. So you have parallel threads, right, running a query. You'll only see one show up in exec requests. In OS waiting task, you might have a parallel worker that's waiting on a latch, but you don't see it in this DMV. So it's important you keep track of this one as well when you consider latch waits dealing with things like parallel queries. Okay, that's just some basics. I know you're at this point, you're sitting there going like, I thought this was supposed to be like really internal and guts and stuff like that. Well, sit back, here we go. What is really a latch? Notice the simplified for non-latch gurus, which I don't claim to be one, I just work for Microsoft. First of all, a latch is really, inside our code, a C++ class. That's really what it is. We have a class we've defined that defines the structure of a latch. Now, what I'm about to show you is the breakup of what this class looks like. Now, it's important you understand this is for 64-bit systems, because if you've ever dealt with pointers or memory addresses, in a 64-bit system, you have 8-byte pointers, and a 32-bit system, 4-byte pointers. Well, this is all about 64 bits, so you can kind of adjust as you need to when you look at it. So first and foremost, at the top of this class is a list of waiters. So if you were to break this class down in memory, you'll have an actual list, if there are waiters, a list pointing to a linked list of tasks that are waiting on the latch. And if you are waiting in the latch, we actually use internally an SOS event, which breaks down to a Windows kernel event to actually wait on the latch structure itself. Now, 8 bytes into this structure is the owner of the latch. It's actual a task address. So if you look at sys.dmos tasks, there's a task address column. That actual address will show up in this structure in memory if there's an owner for the latch. Then there's something called the count 8 bytes later. The count represents the true latch itself. I'm going to show you what the breakup of that looks like in a second. And then after that, 8 bytes later, is the actual latch class, which includes what's called a latch ID. I'm going to show you how to look at a latch ID and figure out the name of it just by looking at the number. Now, get ready for this. If you're not used to looking at bit masks before, you guys said you want internals, I'm giving it to you. This is what the count breaks up into. The count is an 8-byte value that we break up into complex components to make up what this latch looks like. This is important for you to understand because we're going to see an example in a second of how I break this up. These first 5 values to the right, if you read it from 0 to 64 this way, it's 64 bits of data. Each of these represent a single bit we can turn on in the latch. The first 3 are mutually exclusive because they represent ownership. If you own an update latch, we'll turn this bit on. If you own an EX latch, we'll turn this on. Just what's called the destroy latch, which I'll talk about in a second, we turn this bit on. So I won't have any of these, I won't have more than one of these on at once, basically. This bit for wait just means I've got waiters. You don't look at the list necessarily, you can just quickly look at the bit and determine if anybody's waiting on the latch. Now this other stuff, don't even worry about it. Only know that at the far right end is not necessarily a single bit on shared and keep latch, what's called keep latches, but a count. Because, as it turns out, we'll talk about these modes of shared and keep, they're shared concepts. So not just more, so more than one person shares the latch, we'll count the number of guys actually in those states. So that's what the breakup of the count is, and I'll show you an example later of how you can look at this count value and break these bits up and understand, is it owned by an exclusive, is it an exclusive owner, is there waiters on it, and so forth. So when we think in terms internally in Microsoft of latches, when we're debugging things with your code or your dumps, we look at this value and break these bits apart. Is that internal enough for you? It gets worse. No, it's not that bad. So why do you care about that? Well, let's talk about concurrency for a second. I mentioned that latches have this compatibility matrix like locks and modes to them and how we acquire the latches. So this is the breakup of this table of the compatibility. But let's talk first about what we call a mode of the latch. So when you see the word page latch underscore something or latch underscore something, it's one of these 2-letter characters. And this is what they mean. KP is something you're never going to see. It happens too quick in the server. It's used for reference counting, just to kind of peek at a structure that we're using. It's not meant to actually read the structure. But it's important to know about because we actually use it internally in the server, and there's a compatibility with other types of modes. And you should know that it's not coincidental that I ordered it this way. The ordering of these modes start here at 1 and go to 5. We'll actually see in the latch timeout message, we'll see a number. Don't you love when we put numbers and error logs, and you're like, what does that number mean? Well, now you'll know. So when I show you an example in error log of a latch timeout, it'll be one of these numbers, and it starts from 1 and goes to 5. A shared latch you see all the time. That's just for reading. Okay, we're just reading a latch, but it's a shared concept. So we don't track ownership because you don't own it. You're sharing with other people. We just track the count of them. But an update and exclusive latch have ownership. In the case of update, we can allow, just like in locks, we can allow readers, but we can't let anybody else to write to it. And of course, exclusive means it's all mined. I track ownership. No one else can actually write or read from the latch. And the heaviest latch of all is called a destroy latch. Another one you will not likely see in your DMV output. But understand that a destroy latch is used for actually removing something from a structure from a list, like removing a buffer from cache. So if you look over here at our compatibility matrix, you can see, for example, if I have an exclusive latch, the only thing that can actually be acquired is a keep latch. That's because I'm just changing the properties of the structure that's being protected. I'm not destroying it. So therefore, somebody can actually go look and see that it still exists. Now, a couple other concepts about concurrency. We have this waiter list that's in FIFO order, but it doesn't always occur in FIFO order. Why is that? Well, that's because you could have a scenario where a guy owns an exclusive latch, right? And the waiter behind him and the first person in line is the shared latch. So they're not compatible, so the shared latch has to wait. Well, behind the shared latch is another exclusive latch, and behind him is another shared latch. When the shared latch gets its turn to acquire the latch, we'll look at the line and we'll say, can anybody else meet that requirement? We'll let him jump ahead. So it's not always done in FIFO order, but we do guarantee that we don't starve the exclusive latch guy waiting, because we always bump him up in the line to make sure he gets at the head of the list. Okay, let's talk about the buffer latch. You probably just made the assumption that you kind of know what a buffer latch is, what a page latch is. Well, let's go a lot more internal of what actually that is. I mentioned before about shared latches being for reading, and that's exactly what we use shared latches for buffers for. We use it for reading pages. We use updated and exclusive latches for actually changing and modifying the page. And we use a keep latch for just traversing a list of pages that exist in the cache. And a destroyed latch for freeing a buffer from cache. So in the system, we call it a page latch and a page IO latch. I'll tell you about the distinguishing between these two in a second. But why don't we call this page latch in our nomenclature? Why do I call this a buffer latch? Why do you say a buffer latch timeout? Well, here's why. We're not actually protecting the page, 8K page in memory when we do this latching concept. We're actually protecting another structure in memory that you don't normally see called a buffer or a buff. And there's a makeup to this structure that's really important. This is kind of like a C++ class in itself. Let's talk about what that looks like. So the very first member of this buff structure is called bpage. That is actually a pointer, a memory address. So the pointer of the bpage actually points down to the actual memory address of the page in cache. Not a page number, but a pointer to the page in cache. That's how we link these structures together. Now I listed mHeader version over here as like at the very beginning of this. The reason I did is when you look at DBCC page, mHeader version in the list of fields is not the first one listed. But in memory, it is actually the very first field in the page in memory. So if you're ever trying to like dump out the page in memory and look at DBCC page and figure out the alignment, this actually is the first one and not as listed in DBCC page output. So bpage is an actual memory address pointer to the page in cache. Later down in the structure is a bpage number field. That points down to the actual page ID. It's not a pointer, it's a value. The bpage number is a page ID. The mpage ID is the one of the page header in cache. Now what about this bstat value? Another bitmap. Oh, Bob, you're killing us with bitmaps. Yeah, that's what we do for a living. We actually look at these bitmaps, right? But there's meaning to this, and it's very, very important why. If you look at a couple of these bits here, let me point out a couple that are interesting, like buff.io. When this bstat value has a value of 4 set in it, it means we're in the process of reading the page in from disk. We'll look at an example of that in a second. If we've actually modified a page, the bstat value will have the value of buff.dirty, which means the page has been modified but hasn't been flushed out yet. And then what's really interesting is this buff.io error. You ever seen a checksum error occur in your system before? Well, the way that works is that when we read the page in from disk, when we try to go latch the page, if we determine the checksum's bad, we actually mark this buff.io bit in the buffer header itself. That makes it more efficient for us to actually go feed that checksum error back to you as you run into the problem each time. So that's these different values of bstat. We're going to show an example here in a second how we break that down. Now, later down in the structure is the actual latch class. Remember that thing I just showed you with the different 8-byte values? This is the actual latch class to protect the buffer structure inside the buffer itself. I listed another field called blog. I'm not going to talk about what blog means. The only reason it's important is because in memory, this value is the one right after the latch class. And when you look at a DBCC page output, you can find the blog value, look at it, and when you dump out this buffer structure, you can go find it and know that the latch is proceeding right before it. Okay, let's show you what I'm talking about here. Okay, so I've got a DBCC page output here. Does anybody know what page 1 is in master of file 1? PFS page. PFS page. That's very, very good. This is a test. Okay. So when I dump this out, there are probably aspects of this output that you absolutely never pay attention to. Okay. Number 1 is this one right here. Who ever pays attention to what the heck that means? Buff with some address. That is the memory address of this buffer structure in cache. I'm going to show you that in a second. Okay. bpage is what I told you earlier. That's the actual memory address of the page in cache. All right. Can you see here down below here how this value lines up with that value? This is the page, the address of the page in cache. This B page is the pointer down to it. That's how we link the structures together. Okay? Remember I mentioned about bstat. This is the value of bstat. Now, I didn't show you all the bits in bstat, but I showed you some of them. Okay? Now, get ready for some binary arithmetic. You see the hex value B at the end of this here. Let's take B and let's crack it out. If you take B and you crack this out, okay, you get these binary values. And if you've ever done binary arithmetic, it's really easy to put these together. You just take 2 to the power of each of these placements and you add them together. So 2 to the 0 is 1, 2 to the 1 is 2, and 2 to the 4 is 8. So if you add these together, you're going to get B. Okay? So what does that mean? If you go back to our chart here, you can see 1 means on LRU. It just means we're actually using the buffer. What was the other ones we had? Do you remember? 2, dirty. The PFS page is dirty. It hasn't been flushed. And 8, which means it's hashed, which means the buffer just exists in a hashed list so we can find it in memory. Does anybody know why a PFS page would be dirty in cache? Like in my case here? Well, it could have been. Andrew said, he said, I've inserted something in heat. The reason why is you allocated something. It's a PFS page, right? We have to go mark into the PFS bits that you allocated a page, all right? Or some page got modified, like the percentage of number of rows free in the PFS are done. So that's why it's dirty. Now, just to show you how this can actually change with a simple little command here, all I need to do is go checkpoint master and go run this again. And you notice this now changes to a 9. In the back, guys, see that back there? This is now a 9. Okay? A 9 is simply taking away the dirty bit. Now the only bits left are that in fact it's on LRU and it's hashed. So by looking at bstat, you can actually see those values. Now, what about this whole thing I talked about blog and memory and things of that nature? Remember this address I said, which is the buffer structure here? What Bob Ward presentation would be complete without the debugger? Okay. Those of you who want to tweet, like in the middle of the talk, like Bob's got the debugger up, go for it. Does it feel like that happens all the time when I do these? So I don't have private symbols loaded, though, just as you wouldn't. For me, I can do this at work. I can dump out these structures easily. Okay? But if you don't have private symbols, you can actually figure this out. So I'm going to dump out this structure in terms of bytes. Remember the blog value here? 3215979. If you go over here, there it is right there. 3215979. These bytes here represent the latch. Now, a bunch of them are 0. Why is that? I thought this thing had ownership and waiters and all sorts of like that. Does anybody know why it's all mostly 0? Nobody has it latched. Nobody's using the page right now. These values only make sense in the middle of a problem, right? While somebody's reading it, or if you have a long latch contention issue. But there is one value here, 21. That actually represents that thing called latch class I talked about. Well, what the heck is 21? I don't know what that is. You have some lookup table magically at Microsoft, Bob. No, you can figure it out too. If you go hex 21 and turn that to decimal, that's 33. These represent a series of IDs that you can look up yourself in DMV. If you go down in here into DMOS latch stats, and you just dump it without any ordering at all, it would help if you restart the debugger. If you say go, otherwise you're going to be stuck forever. If you look down here and you go to row number 33, you will find this is a buffer. There you go. So a latch class ID of 33 means that this latch, this structure, is associated with a buffer. A buffer is equivalent to a page latch. All the other 144 are something different, which we'll cover in a second. So there you go. You could actually do this at home and prove to everyone that you too can debug latches in SQL Server. What you would use that at your job, I don't know. But many of you have said this is the kind of stuff you actually want to see. Now, I have some more practical uses of these things in a second. Okay. This is one I think you'll actually really like. So a lot of people have asked me before, we have row-level locking now, Bob. I mean, what's this latch thing? Why do we even actually need it? Let me give you an example of what I mean. Okay. So what I have here on the left side is just a simple view of a page in cache for SQL Server. All right. You got page 100. I don't show all the headers of the fields of the page itself. But most importantly, I do show this one, M3 data, which you can see in DBCC page. You can see this header, this value yourself. Well, what does that mean? Well, let me show you parts of the structure of this page, and I'll explain it. So down here at the bottom is something we call the row offset table inside a page. And it starts at the end of the page and goes backwards. What that represents is the byte offset of where this row starts on the page. Okay? So at byte 96, we have this row. At byte 111, we have the second row. M3 data is the byte offset of where to go put the next row on the page. Pretty simple. Here's where you put the next row. Here's where these rows exist. All right? So now you all figured that out. Let me show you this scenario, why latching is important. You want to insert a value 3 and 300. Pretty simple. The server allows you to get an intent-exclusive page lock on page 100. That's really what you need at this point to go insert to this page. You come along and you put your row right there because that's where free data told you to put it. But you're running on a really super fast multi-core system, and as part of this operation, you have not finished your insert yet. Another guy comes along and says, I want to insert my row. I also get an intent-exclusive page lock on this page because that's allowed. Because we're doing row-level locking, right? He inserted his row, I get to put mine in there. Where do you think, at this point, his row is going to go? It's going to go right on top of his row. Because we haven't done any other protection for the page. We both were allowed to get this type of lock. He was allowed to go on top of mine. Now I have lost my data. That is the world without latches. Okay? This is why we create this concept. So if you were to go get an exclusive latch on this page first, and you were to come along and get an exclusive latch, you will wait on him. He is now allowed to go first. He puts his row in. He goes and updates this offset table for where his byte should go on the page. He updates where the next row should go. And he's good. And he releases his latch. He's now allowed to run. He comes along. He correctly now puts it in the right location, puts his row on the offset table, and now we're all good. But in the most simplest form, I mean, it's amazing how many times I've shown this diagram to people, and they're like, I get this now, right? Now, here's the important point. Row-level locking is all about inserting your row, okay? We have other parts of the page we must maintain to keep track of all this stuff. So if we don't latch the page internally, it's a quick operation, right? Then we can't protect each other on it. And in fact, as it turns out, some page changes we make are just in the header itself. For example, when we write in the checksum bits in the page header or the torn bits on a page, or we start doing torn bits in the page header, we just have to change the header. So there is no lock for updating the checksum value. We have to have another way of protecting that page from other threads. So you can see now kind of why you have to have these buff latches, or else you would kind of collide with them in a multi-thread system. Okay, so here's the next concept. The next concept is that a lot of people have come to me and said, Bob, I know what a latch is. It's an I.O. thing. I'm like, well, that's partially right. It's really not just an I.O. thing, but that's a lot of time where you see the visibility of these things, and there's a very good reason for it. So let's talk a little bit about how that works in our system. First of all, if a given worker thread wants to scan a table, table X, as part of the plan, we go down to the engine and say, we need page 100. That's part of our table, right? Let's assume for a second that page is not in cache. So we have to pull it from disk. So here's what we do inside the engine. We acquire an EX latch on the buffer. Now, remember what I said about the buffer structure and the page. There is no page at this point, right? There is a page address in memory, but we haven't filled it in with any data yet. So we acquire a latch on the buffer itself, the buff structure. We can get a hold of that. Now, why do we acquire the EX latch on this buffer? Well, we actually have to modify this buffer before we do this full operation. We have to fill in the page number for the page ID we want. And remember that bstat value I told you about? We've got to go actually populate that to mark the fact that it's in I.O. So we acquire this latch in the buffer. We then post our read asynchronously. So we do an async I.O. to the disk. Now here's the part that's kind of confusing for everybody. We then acquire a shared latch in the buffer right after that. What do you think will happen if I have this EX latch buffer and I acquire this? Anyone? Wait. Okay. I wait. Because they're not compatible, right? If you look at the table, you cannot get a shared latch buffer if he owns the exclusive latch in the buffer. Now, why do we do this? It's kind of weird. Well, and by the way, when you have this property occur, and if it occurs for a long period of time, you see page I.O. latch shared in your DMVs. Let me stop for a second and explain the difference between page I.O. latch and page latch. So the code for acquiring a latch understands what buffers are. It's a very special piece of code, right? And so when you acquire a latch in a buffer, we think normally it's a page latch. But remember that bstat value I told you about? In the latch code, we actually look at the bstat property and say, if that if buffer has been marked as NIO, we will make visible to the users of the DMVs the fact that it's a page IO latch. So it's not two different kinds of latches. It's a latch on a buffer, but it's a different state. The buffer's in a particular state when it's marked as IO. Now, does anybody know why we need to actually block ourselves in this operation?
Because your exclusive latch, when it's done from the ACP's operation, will change your status from IO to complete. So then the share will wake up.
That's what I'm really after more for. Think about the page that's associated with this latch in cache right now, okay? It's not found in cache. It's volatile. We're in the process of going to the disk and pulling bytes and putting it into a memory address. You have no idea the state of what that memory looks like, okay? So if you don't wait on the actual latch at this point, you could be reading bad data. So you have to wait till it finishes. So when the IO completion routine is finished, which could be on a separate worker thread to actually pick that up, we go through and we actually release the exclusive latch. Now, us, and other people waiting on the shared latch can proceed forward and read the page from disk with no problem. Now, what's interesting about this is the fact that we are waiting on ourselves. Okay? And you might have seen this sometimes, the behavior looking at DMVs, other types of visibility things in the engine. You're like, why am I waiting on myself? Well, typically it's because you're actually waiting on a buffer that's being pulled and read in from disk. Okay. Let's move on and talk about latches and Tempdb. All right, let me make a cautious statement here, all right? I will not get into argument with anybody today about how many files should go in Tempdb. Do not ask me that. Do not get into an argument about it. We can talk about it after you want all day after the talk, because it's so contentious of a situation that I'm not going to try to address that. But let me tell you a little bit about why it's important. First of all, the heaviest latch contention I see in Tempdb in my traverses with customers is for allocation. PFS pages, SGAM pages, and GAM pages, okay, typically. And why is that? Because everyone, because it's a shared database, wants to allocate and deallocate frequently, right? You're creating temporary tables, you're dropping temporary tables. You're creating temporary tables or variables and procedures that get dropped. You have work table pages that are actually getting allocated and deallocated. It's a heavily used allocation system. Therefore, it makes sense that the hotspots are probably going to be on these kinds of pages. Does anybody know what kind of symptoms, based on things I've told you so far, you might see on contention of these kind of pages?
Latches.
Okay, latches. Great answer, Adam. Thank you very much. So it would be page latch, okay? First of all, you probably see a wait type called page latch. And your wait resource will have a particular property to them. It'll be a page ID that has a particular type of signature. First of all, the database ID is 2. There you go. There's a clue right there. And then the page ID is going to be one of these kind of pages. A fixed interval kind of page. A 1, a 2, a 3, an 8088, and whatever all the algorithms we use to create the GAM or PFS intervals. So when you go look at those pages in a Tempdb resource contention situation, you can try to determine, is it one of these kinds of pages? And then you know you're hitting this kind of type contention. So that's the kind of symptoms you're going to see when you see latch contention on allocation. How do you ease the contention? Add more files. Make sure it's the same size and property. How many do you add? Go ask Paul Randall. Don't ask me. Is Paul in here? He's not in here. So it's fine. There's been all sorts of debate recently actually raging on this topic. So, you know, a lot of people talk about, okay, it's one file per core, this kind of thing. In CSS, we're pretty simple people. You heard about Atlanta this week. You may have seen me in the keynote talk about Atlanta. We got a pretty simple rule for Tempdb. If you've got one file and more than one CPU, we're going to flag you. We know you're going to have contention. How many should you add past that to avoid your contention? Honestly, as many as it takes to reduce the contention, but balance it out. Now, what do I mean by that? Well, on my laptop, when I've had contention before, I've got 2 cores in this laptop. When I went to 2 files, I still had problems. And then I went to 3. And then I went to 4. Then I went to 5. And by then, I'd reduced the contention, probably the total overall time in half by doing that. 5 files on 2 cores worked fine for me, right? But when I got to 6, 7, 8, and even 10, I started getting degradation again. So there's going to be this threshold you're going to run into. I only suggest that you simply test this and determine what's best for your system. One point about trace flag 118, that's a lot of controversy and myths about that. It's still in the code and it's still needed in some situations. If you run into SGAM type contention, which is mixed page type contention, this type of trace flag can avoid some of that and help you out. And it's just kind of one of those things where you have to try it and see if it helps your system. This is a very important point that people get confused on, though. If you have I/O bottlenecks on the disk that supports Tempdb, you can get page I/O latch contention on any page in Tempdb. So people get confused between Tempdb page allocation latching and I/O latching on any page in Tempdb. They see latching Tempdb, they think it's this allocation thing, right? Look to see whether you're getting I/O latches on your pages. If so, it's no different than if you get an I/O latch contention on your normal database. And this is a really interesting point. So I've run into customers before on really high-end CPU systems that have added tons of files, used the trace flag, and still get some latch contention on pages. But it's not one of these pages. And they don't recognize what the pages are. And we'll break it down and look at it, and we'll find out they're system table pages. Because of so much DDL operations are going back and forth in Tempdb, in some cases, the hotspots are on the system tables themselves. What do you do when that happens? Here's my official quote. You may need to redesign Tempdb usage. What does that mean? That means you may have to actually back off your use of Tempdb. Seriously. Or change the way you're doing your design. Because there's no way to avoid this contention at that point. You've got as far as you can go. And the last point you should know is that a lot of people forget about auto-grow. You know, they actually just throw Tempdb out there. They just rely on auto-grow, and they assume they're not going to have any problems. As you're going to see later in a demo I'm about to do, if you don't worry about auto-grow, you're going to run into a different kind of latch contention that has nothing to do with any of this stuff. So there's a couple of points about Tempdb. I want to show you real quick just a small little stress that I built that can actually show off the symptoms of what this looks like. So in the spirit of what I always do, I have a database. I should have it set up always here. Let's see here, Tempdb latching. And the name of that database is... see if this is it right here. Nope, that's not it. Oh, here it is right here. Nope. Let's see here. Oh yeah. So yeah, that's the right database. Sorry. When you create these kind of funky names that I create, I guess you can get kind of messed up here. So I think this one's particularly called Mavs NBA Champs I Wish. Maybe not in my lifetime. So anyways, that's the name of my database. So I basically create a database that has a stored procedure with a table. And then I go into the stored procedure. I go out there and I try to just basically do a bunch of select intos on this table, right? So let me kick this off and just show you what I'm talking about. Now, in this particular case, Atlanta, there's a plug for Atlanta, would have called out my server because I've actually got one Tempdb file and 2 cores. So this command is just using our ostress utility to stress Tempdb. If you go run this find waiters DMV that I created before, this is what the symptoms look like of Tempdb contention. Maybe this looks familiar to you. Remember I mentioned you're going to get a page latch type of contention? In this case, an update latch. Notice the wait resource is 2, 1, and 3. 3 is SGAM. Okay? That's because I only have one file. I'm using the trace flag. I got a lot of contention to get mixed pages allocated in this database, right? So one thing that's interesting here is the following. Notice in the OS waiting tasks that I actually get the address of this page latch. Okay? Now, remember I told you earlier that you'd use that blog value to find out where your latch is? Well, this is the other way to find it. In this particular case, I'm waiting on that PFS page, on the SGAM page, and this is the address of it. This is the address of the latch class itself. But I told you the latch class is buried inside the page, right? So if you take this value here, be a little sneaky, and you go and dump out, let's see, what is that, 2, database 2, 1, 3, right? Whoops. Okay. I've taught you guys how to look at this, right? You can do it. So here is the buff structure. That's the buff pointer. And I said that I had this other value, right? So I can just stick it right here. Now you'll see here, you'll notice that this is the same almost address. At the very, just look at the end of this thing, E500, E558. What this tells you is that at hex 58, offset into the buffer structure, that's where the latch is. That's the pointer into the latch class. So now you know just by looking at this that the latch class is always, whatever 58 is into decimal, bytes down into the buffer structure itself. So I could actually dump this out and see that same values again. The waiters list, the count, the class ID, all those kind of type things. So that's just another way of a technique of finding out where is this latch class inside the buffer structure. So, this is the kind of type symptoms you're going to see from Tempdb, right? If a guy calls me up and says, hey, I'm having some problems, I'm getting performance issues, and as soon as he sends me this right here and I look at it, I'm like, okay, there's Tempdb contention. I just know to look at it because I see the database ID, I see the GAM number. Remember, though, that these numbers could be large, right? The 1 could be a 3 because you have multiple files. The 3 could be some other GAM interval, SGAM interval, or PFS interval. But this is the common symptoms you're going to run into Tempdb stress. If you start adding files, then this stuff will start alleviating a little bit, but you're going to get to a point of no return where you can only get so good at this. And you still, if you sit here and just run this DMV all day long and snapshot it every second, I contend you're always going to get some small weighting on these latches, milliseconds of time, very, very small. The key is, are you getting seconds worth of weighting, or even multiple seconds worth of weighting, or even longer? Are you down to the really low millisecond range? That's really the key to this. Okay. So, I've told you a lot about buffer latches, right? Same thing as a page latch, used to protect a buffer structure inside SQL Server. But I also mentioned to you that we had this concept called a non-buff latch. Now, why do we have something called a non-buff latch? I always thought a latch meant pages. Well, here's the deal. We built this concept in 7.0. The developers that have come since 7.0 looked at that concept and said, that's pretty cool. I don't want to build my own thread synchronization mechanism that have a list of waiters and owners and modes and things of that nature. I'll just reuse that class. So over time, we've done a lot of them. In fact, right now in SQL 2008 R2, there's 144 of them, different types of non-buffer latches in the system. What that means is there are 144 types of data structures in the server that use a latch to protect themselves inside our code. So we're just reusing the buff latch concept to protect other structures other than buffers. If you look at the DMVs, like OS wait stats or exec requests, they appear as latch underscore XX. So you're asking yourself, great, latch underscore XX. That doesn't tell me a lot. What is this really? What is this thing? Well, inside some DMVs, the wait resource will tell you the type or the name, okay? And the actual memory address that we talked about, a latch class memory address, can show up in these wait resources or like in a resource address, okay? As well, you have this DMV called OS latch stats, which lists the names of all the classes and corresponds to what you see like in wait resource or in resource description. Well, what about the other wait types? If you were here last year, I did a talk on wait types. And somebody actually asked me in the clinic, says, you've already done this talk. You did a wait types talk last year. And I'm like, yes, I did a wait types talk last year. But a bunch of the wait types you'll see in wait stats are not latches. And you're like, okay, you're really confusing me now. I thought you said you guys reuse latches to protect other structures. We do. But not all of the structures are protected by latches. It's a concept we use in the server all out, but not all the time. For example, CX packet, which we talked about last year, about parallelism. There's a different mechanism in the engine for them to protect the synchronization between their threads. They don't use a latch. They use something totally different. Async network I/O is simply us doing a wait for single object on an I/O completion port inside SQL Server. We don't use a latch class. We have our own concurrency mechanism. So there are other concurrency mechanisms in these wait types, but they're not latches. That's the key to that point right there. Okay. And the other point I want to make sure you understand is when you do see the latch underscore XX, what is the XX? Does anybody remember what I told you that was? The mode, like KP, SH, UP, EX, DT, those kind of things. Those modes determine the behavior of us acquiring or waiting on the latch. So if you see latch underscore SH and you're waiting, what is the likely scenario? Somebody's got an exclusive latch on that structure, and that's probably why you're waiting. Because we said a shared latch is compatible with an update latch, so it's probably exclusive in that particular case. Okay, so Bob, you just said there's 144 of these things. We use it throughout the engine. Why do you even care about this? Well, normally you would not care about this because, quite frankly, when we built the engine, we kind of built it in such a way that we really don't want you to have to see all those other latches. We specifically added in information about page latch and page IO latch because we knew that you might care about that. It could indicate certain problems going on in the server. But in the interest of being transparent, we actually document all these other 144 classes in the wait types and latch stats. So normally, you don't care about it. But if you're people like Adam Mechanic, you run into problems where you email me, and you do care. And here's why. If you've got thousands of waits with high average wait time on a latch underscore XX and a latch class that goes with it, you care about that, right? Because probably it's going to block you, or it's a big waiter in some sort of blocking problem. Or in the case what Adam and I just talked about a problem here recently, you might have a lot of waits that are short-lived, but cumulatively, in the execution of like a query, they actually make up a particularly long period of time and affect the overall performance of your query. So now you do care, right? Because you see a bottleneck going on in the execution of your query, and you're not sure why. Now, as it turns out, the books online, when it talks about DMOS latch stats, actually has pretty decent description of a lot of these actual latch stats. Unfortunately, though, there's only like a description of like 20 of them. So what about the other 120 classes? They say internal use only. Yeah, I know, that's kind of a pain. Internal use only. And it's, again, because the product team thinks that in most cases, hopefully, you'll never have to worry about those. So what I put together was a little bit of a chart here that talks about other latches you may need to look out for that are non-buffer latches. Thanks to Adam here in the front row, I've paid particularly close attention to this one recently. I've seen a lot of customers recently run into a problem where a nesting transaction full latch has shown up in their query workloads, in their latch dash workloads. We don't know much about this problem. We do know the following, that it's related to the following situation. You've got read committed snapshot isolation on your database, and you're running a parallel query. So right now, I'm actually in the middle of investigating with Adam, is this a bug, or what is this problem, right? Because I've seen this latch show up on a couple of customers where it was just really short-lived and not many waits at all. But he's got a workload where this really affects the overall performance. I mean, he can get rid of this problem using things like no lock hints or changing the behavior of the keys. And I think the problem is like the performance goes down in half by just making that change. Because the most important part of the contention here is the waiting of this latch. And what's happening here in the engine is we're having to protect certain structures that affect row versioning across parallel workers. So we've got to look at that further and find out, is this a bug or is this something we can fix? The next two are really interesting. You're going to see a demo in a second of what those are, so I'll reserve comment on those when we look at those in a second. If you thought that I wasn't done with my internals, I have a pretty exhaustive internal demo, if you can hold on with me here, to show you in a second. And it involves these kind of type latches. This one's really interesting, the access methods dataset parent latch. And I only bring it up because it's not necessarily a case where you can affect its behavior, except for the fact that you only see it during parallel query execution. So if you don't desire parallel query execution and you're seeing this latch, change your plan, change your design of your query to avoid parallelism, and then this will actually go away as a contention point for you. The next two are interesting. Only I've seen these in high workloads and in benchmark testing that's gone on. And that is, we have certain types of structures in the server that deal with allocation. And I'm not talking about allocation pages. I'm talking about a cache that marks information about free extents and free space that we have in the system. So again, they're shared data structures that multiple threads have to access. So there could be contention in high workloads. And what we found out is that typically, if they're causing really major problems for you, it's a sign you might need to partition your table, actually, in those cases. So if those come up as big high wait times, you may need to actually partition your table to avoid the problem.
How would that help if you're doing...
Well, we actually take, the question is how does that help? It's because with the partitions, these caches are all now partitioned out. Each partition will have its own cache, and therefore you've distributed the workload. You've scaled out the sharing now of the structures. So the last one is called transaction distributed mark. The only comment about this one is that we see these in DTC transactions. I've seen a couple scenarios where a DTC transaction, an application wasn't designed properly, and they saw some contention here. But quite frankly, they had so many other major problems, this was kind of the least of their worries. The important point to note here is that just like when we show page latch in wait types as a buffer latch, a tran mark latch XX will show up in the wait types DMV, and that's equivalent in DMOS latch stats to this one called transaction distributed mark. So those are just a couple of examples of ones I've seen customers run into that you actually can have some impact on. If you see other latches, if you see latch XX waits, and you don't recognize as one of these kind of type things, you're probably going to have to open a case with us to look at it, because quite frankly, it's probably a bug or some sort of limitation we just haven't run into before. If you've got other examples of latches you've run into, ones that are really significantly impacting to you, I'd love to hear your examples so I can investigate them. Here's one thing I want you to make attention about that last point. If you go into DMOS latch stats and you just dump it out in your system, you're going to find a bunch of those 144 show up like 1 time, 2 times, 5 times with very low weighting. Okay? If you're just crazy about figuring out what those are, let me know and I'll help you figure those out. But in general, with that kind of type statistics, I don't think they're relevant for any performance going on in your system. So you might see some of the other ones actually in your system. I don't think they'll have a bearing on you. These are the ones we've actually seen that are non-buff latches that could have a bearing on your performance. So, let's debug a latch. You are either at the end of this session going to be really, really upset and crying and your head splitting, or you're going to be asleep in the back. So we'll see. Okay. So let's go through this. Okay. By the way, if you were looking on the past site, like, where's Bob's slides? Where's his scripts? I just finished off this today, so fine-tuned it. I always do that in all my past talks, but I'll have it all uploaded tonight or tomorrow, so you'll have access to this stuff. And like any time I do these talks, if you can't find these things, you just email me and I'll shoot you off the stuff and give it to you. So, I have a database called What a Year for the Texas Rangers. Except for the Giants guy over here killing me. So I've got this database running and set up already, okay? So let me get a couple things going here in my system. I mentioned before about X event, right? I've got an X event session built for you, a script that you can use. And let me just point out the important point here is that the actual event in X event is called latch suspend end or latch suspend begin. So we don't have an X event that tracks all the latches that have happened to the system, whether they get acquired or not. We only have an X event that tracks when you had contention for a latch. Latch suspend in is what I particularly want to track because that's the end of the waiting period that I want to see. So I'm going to kick off this X event session. It hasn't been, I can't drop it because I had dropped it before. That's no problem. Okay, I've got my debugger up and running. And I've got a set of DMV queries I want to show you. These are just basic DMV queries. One thing I want to do is I want to clear my stats because I want to show you guys after I run the scenario, the workload, what the actual stats look like and who was the top waiter in this scenario. So let me clear these guys. Okay. Now I'm going to get ready to run these guys, which are kind of variations. Did anybody notice in my first DMV that I cheated on session ID? I said session ID greater than 50. Not a good idea because, you know, your session IDs can go above 50 for system tasks, so don't ever do that. Try to do the right join here to use the sessions DMV, so I'm doing it now the proper way. If anybody says later, Bob did it the bad way, here's the proper way to do it. So if you run this DMV here, this is just going to give you basic information about the waiting. Excuse me. So I've got in this directory here in debug a latch, I've got this repro CMD file, and what this is going to do is it's going to do a bunch of inserts. Okay? I'm going to fire this guy off. And I'm going to go run my queries here. Now, let's go look and see the properties of these real quick. And I need to show you something. So, I told you to look for wait types. I've got some. I've got a latch XX, and here's the resource. FGCB add remove with an address next to it, okay? Now, if you'll notice here, the blocking session ID is 57. So 57, this guy here, is the guy that's blocking me. I'll get back to that in a second. So we know we have a contention problem on this type of non-buff latch. And some guy doing some sort of preemptive OS something is the guy blocking us. Now, I told you before, we could take this neat little address right here and we could do something with it. And I'll grab the address actually down here. And since you all are just expert debuggers, we'll just break in here. We'll dump that out. Now, before, I dumped out a buffer structure in which the latch was part of it. In this particular case, I'm dumping out directly the latch class itself, which is part of this upper level structure called file group control block. So I'm not dumping that. I don't care about that. I just want to see what the latch looks like itself. Okay. Now, you have some important properties about this. Let's go back real briefly and look back here at this diagram right here. Remember this thing? This is a breakout of that class. I have waiters, an owner, a count, and a class. Let's see if we can actually figure this thing out. Okay, this is a 64-bit system, so these are 8-byte values. This first one here, that's my list of waiters. Now, I'm not going to dive into that, but notice it's non-zero, which means I actually have people waiting. This one's interesting. This is the owner. I told you before that the owner would be a task address. We'll go back to that in a second. Okay? Now this next one has an A. That represents the M count. Remember I said the M count is a bitmap. Do you remember that? So let's pull up calculator, because you guys have this just sitting around all the time and you use calc. There we go. Let's do an A. Okay? And let's break it down into the bits. Okay? Now I want to try to pull this off here. Let's see if we can do this. Let's do Shift F5. Whoop, that's not what I wanted to do. Let's go back. Actually, we'll just make it quicker. Go here. Shift F5. Okay. Let's bring up calculator. Okay. Maybe you can see this bit line up here. So, this up latch bit is 0. We don't have an update latch. But the EX bit is on a 1. Somebody owns an exclusive latch. The DT latch is 0. That's what I would expect. Remember I said these 3 bits cannot all be 1 at once. In fact, only 1 can be on. And the next bit says wait, a 1, waiters. So now that M count is, in a sense, our latch that we use to show who owns what and how it's protected. So you have an exclusive owner, and you know you have waiters by the bit being on. That's a breakdown of the actual M count. Now, what about this number 37? You remember before we looked at the buffer structure, it was all zeros except for a 21? I translated that to a decimal 33, and that was the DMOS latch stats class ID, right? Well, let's do the same for 37. Let's take 37, break it into a decimal, which is, 37, this is 67. Wait, sorry, octal. Decimal. Sorry. This is 55. Let's go look at our latch stats. Oh, what did I do? G. The common mistake of any escalation engineer. They call my desk and they go, Bob, my server's hung. Hit G. All right, 55 is FGCB add remove. So you can see the latch ID stuck in that structure lines up with this number and that name, and that's the name we saw in the resource description. Now, let's go actually, we've actually gone and we've broken into this latch class. We've seen actually this. What about this right here? Remember I said this was the owner? Let me copy that off. And I told you guys that was the task address. Am I right? Well, let's go back up here. Oh, I think I might have. Okay, so I lost my result. Let me run. It's probably already finished. So let me just quickly run this again. This will just take a second. And not make this to be a hard repro to run. You just got to drop the table and recreate it. Now the reason I got to recreate it is because auto-grow is already finished. So I got to get back to the state again where the database is recreated to get the grow again. I could run a scenario where I grew a bunch more allocation and got grow again, but I don't want to do that for this case. So what I want to show you guys is, now it's going to change. I got to go to the debugger again because this value is going to change. So I just got to get this running so I can see it. I run my repro. I go run this. Now, I want you to pay attention to that task address. This is the guy, this preem OS write file gather. So I'm going to copy him out because I'm going to need him in a second. Okay? I'm going to go to the debug. Well, first I got to go find my resource address for my latch, which was down here. I'm going to copy him, go back to the debugger, going to dump him out. Okay? Remember this value? That is the owner. This is the waiter list. This is the owner. So I'm going to take him. I'm going to copy him. And I'm going to stick him right next to him. And there you go. It's the same address. So that's the owner. And now I can prove by looking at the debugger that inside here, the owner of the latch is the head blocking guy. Have you guys seen this before? This particular scenario. And do you know what it is? Have you ever seen this preemptive OS wait type? Please, somebody last year remembered my session? Autograph. Autograph. Autograph what? Does anybody know? Data. Good try. Actually, Adam is technically correct that this actual preemptive type can show up both for log and for data. But the key is FGCB add remove only shows up for the data. Now in this particular case, does anybody know why autogrow took a long time for the data? What type of feature in SQL am I not using? Instant file initialization. Now I got a little tricky on you guys. My service account actually has the permission. There's this handy dandy little trace flag, 1806, that I don't tell you guys about, where I use for testing purposes. If I turn that on, I kind of turn off that feature. So by turning on trace flag 1806 in my little repro script, I turn that on first. I bypassed instant file initialization, and therefore autogrow took a long time for the actual data itself. Okay, so now you guys get a feel for this is the kind of type scenario you're going to see. You're going to get some sort of non-buff latch you've never seen before, and you're going to have some lead blocker, and the resource and the task address line up to the ownership piece. Now there's another scenario that I have in here I'm not going to go through and run for you, but that does deal with thetlog autogrow scenario. And what you're going to see in that case is you're not going to see FGCB add remove. You're going to see a different one. You're going to see this show up as, and I'll show you in the next slide here. I guess I have it on the next slide. Let me get back to this slide. Shift F5, Bob. Shift F5. Shouldn't PowerPoint just work? I mean, now I love PowerPoint. I shouldn't say that. But I thought you might find this interesting about just autogrow in general. So FGCB add remove latch waits are data. Okay. Log manager latch waits are log. You know, you're sitting there going like log manager. I thought that was kind of like a write log or a transaction log IO. Internally, we call it log manager space. Why do we call that externally log manager space? I'm not really sure. But you can see why. It's a latch that protects structures that manage the space for the log. So if we're trying to grow it, we're holding onto that latch to record information about how big the log is, and therefore you're going to get contention on that kind of latch. It's a data structure associated with space for the log. And often the lead blocker is this guy right here, preemptive OS write file gather. This is the actual API call being made to extend the file. There's also another one called file ops you might run into in some cases. This is the one I see the most. But don't forget that often another symptom of autogrow is something you see in the event log. Let's see if I've got that actually. Let's just do this. So if I go here in my event log and I try to filter on event ID 5144, let me zoom in on that. This is kind of a nice thing we added a while back. You may have seen it before. But when we try to auto-grow a log, okay, and it gets canceled or timeout, or it actually takes a long period of time, we'll put these warnings in the event log. 5144 and 5144, 5145. If you find these things, this is kind of an after effect. Maybe you're not monitoring your server and seeing the fact that you've got these different latch types I'm talking about, but somebody says you had some really wicked performance problem, and if you go find these in the log after the fact, you'll know that's probably what happened. So when you see these kind of events, absolutely it's one of two cases. You had the FGCB add remove latch or the log manager latch. You could go back to latch stats and see if there are big waiting times occurring on those two latches. And in fact, we can go back here. Once I hit go, let's see. If we go back and show the stats here, I can see number one, notice I have a big wait time on latch SH. What the heck is latch SH? I don't know. So I'll go to latch OS stats. And I'll notice, this is interesting, right? I got a lot of waiting requests on buffer itself, but not a big average wait time. But look at the wait time I'm getting for this latch. So it's a lower count, but who cares? It took all this time. I only had 3 or 4 guys waiting in this thing. The buffer latches are occurring frequently, right? I mean, if you see small, you're going to see wait requests and small wait times on buffers. It just happens naturally as we're running. But when the average wait gets really large, that's when you're going to start paying attention to, are these max waits. Notice in this particular case, the max wait in milliseconds was 307 seconds. That's pretty long to affect my query. Okay. So, let's talk about latch timeouts. Latch timeouts are really, 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 really bad. Why is that? Because if you're seeing in your system the DMVs, you're getting wait times and wait types for latches, whether it's a page latch or a non-buff latch, and you're seeing milliseconds, or even sometimes it gets into seconds range. That's really interesting. But what happens in the engine, we've been doing this for a long time, way, way long time we've done this. When we actually see a latch that's waited 5 minutes, which is that long of time, we dump something to the error log. Okay? And this is how the logic works. Number one, if we have a buff latch timeout at 5 minutes, we typically, in most cases, will dump this message out to the error log, and I'll show you an example in a second, and then we'll actually raise an error back to the client. We don't wait any longer. We wait the 5 minutes. We print the warning out. We fail whatever you were doing, and we return an error back. So these are seen in combination. This will show up a warning in the error log, and you'll get an error 8:45 back to the client. Okay? However, in some cases for buff latches, we'll be in some critical operation, like rollback. All right? And in that particular case, if for whatever reason, because of some problem in the code, we run into a latch timeout, we cannot fail at that point, right? Because we're in rollback, for gosh sakes. That's a critical part of the code. So we'll have something called a continue waiting latch, which is a different warning. It looks similar, but at the very end it says continuing to wait. If that continuing wait lasts for a really, really long period of time and it keeps going and going, you probably have a hang of your system at that point. Now, message 847 is a non-buff latch timeout. And we always wait for that forever, actually. There's no stop to those waits. There's no error or failure scenarios. Does anybody know why we can probably afford to time out normally on a buffer latch, but not on a non-buff latch? Communicating an external resource. It's all about critical parts of the code. If you get a normal buff latch timeout, you're just running a query, like you're selecting data or something like that. Well, if you're on the middle rollback, we can just roll you back and fail your query. If you have a non-buff latch, like one of these access method things or something like that, we're typically not a part in the code where we can safely do that. We just have to wait until it finishes. So sometimes what you'll have are these non-buff latches that'll be running. You'll see them in the error log as a latch timeout, and it'll take forever. It's probably some bug or something going on the server that we have to go investigate. But that's why we always have to wait here. But it's a different type of message that shows up. The question is, XP command shell a real bad victim at? And the answer is that's not a latch. That's a different wait type. Remember I talked earlier that there are wait types you see in wait stats that aren't latches. That happens to be one of them. Okay, so because the CSS team bugs the dev team all the time to say, look, you got to give us more diagnostics when these crazy hang scenarios occur in these latch timeouts, we will produce a stack dump often in these timeout warning scenarios. It's a mini dump, but it includes special information in the dump for what we need to debug the problem, like the latch structure or the buffer structure or things of that nature. There's limits, though, on the stack dump. We don't like dump every single time. So if you were getting like a latch timeout every 5 minutes and we're waiting, you just get it over and over and over, we're not going to just keep throwing stack dumps at the system. There's also scenarios where we exclude doing this. One of them I just showed you, FGCB add remove and page IO. We don't do stack dumps because we know those are scenarios that could take a long period of time based on some sort of design of your system. There's no reason to get a stack dump because we know from these types that it's a known signature of our problem we can go debug. We don't need the stack dump to go figure out the problem. And then there's something called a dead latch. You ever heard that term before? It's a dead latch. First of all, it's not your fault, okay, if you get a dead latch. It's our fault, typically. And it's typically a hang. Sometimes you'll see a buffer latch timeout that lasts forever, and it's like a hang of the server. The most common thing we've seen is a self-dead latch. What the heck's a self-dead latch? Okay? A self-dead latch is where we're waiting on ourselves, but it's not an I/O scenario. So we've got some sort of like typically a non-buff latch where we go get an exclusive on it, we turn around and get a shared later, and in our own code we never resolve it. Okay? That's a self-dead latch. And I actually have the speaker notes. I'm going to give you guys all the speaker notes in there. I've actually got a KV article for a known bug where you actually get in this self-dead latch scenario. Let me show you some examples of what some of this stuff looks like so you can get a better feel for it. Are you guys hanging on? I mean, you got 20 minutes. 20 minutes, right? When does GameWorks start? 7, 6, something like that? Like now? Bob, stop so we can go to GameWorks. Yeah, can you adjust the time, right? There you go. So here's an example of a buff latch timeout, okay? Whoops. Okay. So, let me turn word wrap on here so you can see this whole thing. Can you see it in the back, or I need to zoom it? Zoom it. Do it, Bob, do it. Okay, this is a timeout you'll see for a buffer latch. Now, remember I taught you guys all this great stuff earlier about codes and types and numbers? This type is the mode. KP1 shared 2. It's a shared latch. That's the type. Okay. The BP, in the case of a buffer latch, that's that buffer address I was telling you guys about. So right here, there's the buffer address. Here's your page number. What is the stat value, can you imagine? What do you think that is? It's the bstat field I told you about. And D, you see the D broken out right there? If we were to bust that out, there's a special bit. I'll tell you in a second what that means, all right? You have your database ID, the allocation unit ID, so you know what table this belongs to. You have the task address itself. This is the task that's waiting on the latch, that's timing out. The wait time is 300 seconds, which is 5 minutes. I calculated that real quick. What do you think flags is? Whoops, ooh, that's terrible. Sorry, need to zoom it in. Flags is mcount. Why couldn't we just call it mcount? Flags is the mcount field. So we could break that A out again, and we could figure out, do we have an exclusive latch? Do we have an owner? Do we have a waiter? What are the properties of the latch itself? So that's how you actually break out that value. And then you have owning task, right? This is the task of the person that owns the latch itself. The task address, as you see the DMVs. And then you remember I told you before about this special extra thing at the end of the message, not continuing to wait. So in this particular case, we had a buffer latch that we didn't have to wait on, okay? So we just timed the thing out, failed back to the client. In the cases where we have to wait, it'll say continuing to wait, and we'll just keep actually waiting. Now, what can I tell about this kind of latch? I said I had two kinds of buffer latch problems. A buffer latch and a page IO latch. Page latch, page IO latch. How do I know from these messages which one it is? You could break out this bstat right here. And you would find that 400, okay, means we're reading the page. And a bit for D means it's in IO. It's one of those bits. So you could bust this out if you wanted to. Or in the case of this customer, you could actually see messages like this. I actually purposely hid this from you. You had a message like this. SQL Server encountered 95 occurrences of IO requests taking longer than 15 seconds. As it turns out, the database for this is the same database for the buff latch timeout. So this is one of the nice things we added in the server, of course, to warn you about IO delay. This does not necessarily mean, but just by looking at this, that you can tell the problem that is a buff latch, but you can put 2 and 2 together. If you're going to get a 15-second delay in reading a page, you're going to have a buffer latch timeout. That's going to happen. Okay? Sorry. If you have a buffer latch timeout of 5 minutes, you're guaranteed to get one of these on IO, right? Because this is 15 seconds, but a page IO latch is 5 minutes. So an easy symptom, when we look at this and look at your error log you sent us, we get the page IO latch, buffer latch timeout. We see this, we're like, it's on the same database? Sorry, Mr. Customer, it's an IO delay problem, right? There's no reason to go debug this any further. So what about a non-buffer latch? Well, as it just turns out, I've been running some scenarios on non-buffer latches, right? Do I have one of those things in here? Well, yeah, I probably do. Okay? So I'm looking for 847. Sure enough, I've got one. Notice that what this property looks like. Time it occurred waiting for latch class. It looks slightly different, right? Because it's a non-buffer latch. There's no reason to have a BP pointer or a page pointer. Now, the ID field is interesting. It says ID, but that is really the latch address. Okay? That is the memory address of the latch class. If we had our handy debugger up, we could go dump that out, and that would be the actual latch class itself. In addition, the type is the same mode. It's a 2. It's 2 means shared. You have the task address. The flags is still mcount, and you have the owning task. And this is continuing to wait. So this is an example of what a non-buff latch would look like. Now, as it turns out, I told you we did stack dumps. But we have exclusions. This is one of them, because we don't need the stack dump. So in some cases, you'll get a non-buff latch timeout with a big stack dump to the error log. What do you do with that? Call me. And I'll help you look at it. Okay. I hope that's not the game works. Okay. So how do you know latches? Let's just summarize a couple things about latches causing you problems. Okay. Number one, page IO latches, I should say page IO latch, not page latch IO, equals IO bottleneck. Okay? Customers call me with this is in the seconds range. But what is the average disk transfer rate of a decent disk? Milliseconds. 10, 8, whatever, not seconds. Don't call me and say, Bob, I don't get the thing. Why? What's seconds? Why is that a big deal? Well, your disk should be a lot faster than that, or your drivers, or whatever your system is. And not always a high count is always as necessarily a problem. It's usually actually the actual latency you're seeing. Okay. High buff latch weights mean usually hot pages. Now, have you ever used this DMV before? It's pretty handy. I've seen some blog posts recently about it as well. SysDMDB index operational stats has certain properties in this DMV that calculate and tell you how many page latch weights you had and page IO latch weights you had per index. So you could actually run queries to find out what are my hot indexes in terms of latch weighting and specifically IO latch weighting. What databases, what tables, things of that nature. Now I will say this though, when you have high buff latch weights, that's not one of these scenarios. It's often sometimes a bug, unless it's like an allocation page or one of these scenarios we're talking about that's a hot or IO page. But it could be system table pages for DDL and Tempdb, keep that in mind. Or it could be your own database for DDL for system table pages if you do a lot of allocation, deallocation with tables. And then non-buff latch weights just depends on the latch class. Find out the hot class by looking at DMOS latch stats. See if it's one of these generally known issues I've mentioned to you, and then take the necessary action. And then latch timeouts are just bad, man. I mean, when somebody calls me and says my server's having really, really bad problems, that's one of the first things I look at to see if they're getting one of these kind of things. Often I see these things associated with non-yielding scheduler problems, server hangs, things of that nature. The one exception is I.O. When I always look for I.O. problems, when I see that SQL Server has encountered I.O. delay requests along with latch timeouts, I just discount the message because it's usually an I.O. problem. Okay, one last concept for you. I'm actually going to make it on time today. Might have time for questions, actually. So, buffer latch enforcer. What is this kind of type crazy thing we have? I talked about a buffer structure and a database page, and that's something you need to make sure you fully understand when you talk about buffer latches. A separate structure and a page. Now, if I have this kind of a criminal come along called a scribbler, no, it's not a new comic character or something like that. This is like a thread within SQL Server from a DLL or something else that might be incorrectly writing on a database page and causing access violations and corruption and problems of that nature. Sometimes we see this with customers when they'll have a serious problem. We'll look at it and we'll determine that the page was damaged in cache by some rogue type of thread running in SQL Server. We call them scribblers. So what can we do about that? Well, we have a technique that's pretty interesting. When you turn on traceflag 815 in the server and you acquire a shared latch, we use the virtual protect APIs to mark the memory from Windows for the page as read-only. Because remember, if we've got a shared latch, an exclusive latch would get blocked, right? He would have to wait. So if we're just reading the page, we can afford to protect this with Windows as a read-only. So if our same scribbler comes along and he tries to do this, he gets busted. He gets busted with an access violation because he tries to write to a page marked read-only with Windows. Now this is kind of an expensive operation though, so this is not something you should just throw on your server all the time. Only running into these really strange scenarios. Let me show you an example of actually what the signature looks like. So often, sorry, not often. In my role, often I see access violations I have to deal with in my life. Okay, necessarily mean that you always hit them, but so when I see these access violations, I look for something in particular interesting when I run into them, and that is the following. You see in the stack name it says access violation. But I want you to pay particular attention to these things. Right here, this is the memory address that we were having the problem with the access violation. Now, in most cases, that address does something like 0 or 3 or D or A, because often it's a null pointer reference inside our code. And it's a null pointer offset reference, like we're offsetting a null pointer by 6, D, A, whatever. And it's usually a reading address that I get these AVs on. But one day, an engineer on my team came up and said, Bob, I'm having this problem. I'm working this kind of funny case, and I'm getting an AV, and I don't understand it. It says writing to this address, and that is a valid address in SQL Server's memory space. And so my first question to him is, did you have trace flag 815 turned on? And he said, yes, I did. I was trying to solve this corruption problem. I said, guess what? You found the scribbler. This is how we detect the problem. When this is turned on, we can catch the actual thread writing to that address we've marked read-only, and it'll say writing address, and the address will be good. We can then go look at the stack and find out who was doing this. In this particular case, the input buffer was XP, I'm a good xproc. What? I think in other talks I've called it like XP, I'm a junior programmer or something like that. So, and we can see at the top of the stack that SQL called this xproc, and that's the bad guy. So in this particular case, I happened to carve up an xproc that actually touched a database page. But we've actually seen this before be a code inside SQL Server, our own function code that was actually doing this particular problem. In other cases, I've seen this show up as like, I don't know, MSORA? Oh, I'm just kidding. No, I've seen other DLLs show up in the process space that are running by a link server query, a COM object, an extended procedure, all sorts of things that get loaded, even actual buffer flow over protection filter drivers that get loaded in our process space that could be causing these kind of type scenarios. Okay. Now let me finish off. If you look at the slide deck here, when you get this, I'll just mention there are some resources here for you to look at. There's not a lot of resources on latching, actually, as it turns out, except now for my talk, I guess. So one thing I thought I'd just mention here with some bonus material, since we have about 3 or 4 minutes, is Spinlocks. What the heck is a Spinlock? I thought that was a latch, Bob. So I'm sorry for this slide not being pretty, but it's in my bonus part of my slide, so I didn't count on it being very readable. But I thought I'd just tell you briefly about it. So as we mentioned, shared data structures need thread protection. And Windows kernel object can actually be quite expensive. So I mentioned that a latch uses a Windows kernel object at its lowest level, an event, to actually do the waiting and the waiting on this actual latch structure. So it may be cheaper for some really lightweight work we need to do in the engine to spin instead of waiting. But it has to be very fast. And fast in the sense that it's not going to kill my CPU. So I need to spin as something that's really quick. It doesn't take a long period of time. Otherwise, if I do this spinning operation, I'll have a lot of bad CPU problems. Okay? So SQL Server often will use this spinlock concept on a list, or a bit even, or an integer, like a latch class. We actually have a spinlock in the latch class to protect the access to the latch structure itself. Okay? But I thought you said a latch does that. Well, it does, but it's a little heavier than this. And it's got a lot of structure to it that we don't need for spinlocks. Okay? There's no waiter list. There's no compatibility matrix. You either spin or you don't when you do this. Now, what do I mean by spin? Hey, in the end, it's just a tight loop. It's a piece of assembly code that just sits there and just tests to see if we can get this access to this integer value. And if we can't, we just go back to the top and we just keep doing it over and over and over. Well, to avoid just absolutely taking down the entire machine, we have a concept called a backoff. So after a certain number of spins, we say, oh, we still can't get this resource, so let's go sleep for a while, usually literally using a Windows sleep call. That's called a backoff. So when you see in the DMV DMOS Spinlock stats this backoff column get increasingly big, that's when you should care about it. Because that means we have a heavy contention on Spinlock. You may have heard of a famous situation called the token perm store cache in SQL Server. That problem was based on a poor design of using a Spinlock. And what would happen is you'd see a mutex Spinlock show up in Spinlock stats. It's not an NT mutex. We name these Spinlocks certain names. And this one we have, it's a generic name called mutex we use in several places. And the signature for that token perm store cache problem was high CPU, right? You guys killed your CPU. What was going on is we had huge contention on this mutex Spinlock. So we had all these threads out there spinning around, right? Because it was not actually scaled out in a way we designed it. We actually changed that in SQL 2008, so it's a little bit better of a scenario. But this is kind of what a spinlock is. It's a very lightweight way of protecting data structures, not as heavy as a class. It still has the same type of concepts and properties. It's a particular piece of concept that we built in the engine. So, we're about to hear the end of our talk. We've got about 4 minutes left, but I'll let you go a bit early. Please, I really take these sessions really seriously, and I take your evaluation seriously. So please take the time to fill out these forms to win your laptop. Thank you for your time.